Can you hear me? Yeah? Okay, so hello everyone. So I guess I should start with, I'm not really working with conditional lower bounds, so I cannot really tell you that much about that. So I'll be talking about string problems, and I will try to focus a little bit on the conditional lower bound aspect, but I mean, there's only so much I can do. So please feel free to ask me questions and interrupt. And so the first hour should be quite simple. I will talk about some basic things that maybe you have seen already. And then we will move to some more advanced things. So today I'll be talking about approximate pattern matching. So what is approximate pattern matching? Okay, so let's start with pattern matching. So pattern matching is probably the most natural question that you could ask when you think about text data. So you have a text T and a pattern P, and you would like to check whether your pattern occurs in the text. And I will show you an example on the next slide to make sure that we're on the same page. And if the pattern does occur in the text, you would like to find maybe all of its occurrences, or maybe just the leftmost occurrence, or maybe just yes, no. Maybe you would like to know whether they exist or not. Okay, so what do I mean by text and the pattern? Because it's not so clear at this moment. So by a text, I mean just a sequence of characters. So I have this example. So it's a sequence of characters. Yeah? It's not a natural language text. So just a stream of characters that I had to break into lines. And your pattern is also a sequence of characters. And the goal is to find this pattern in the text. Okay, so that's the question. And when you stare at it for some time, you will start to see things, and hopefully I didn't make a mistake. There are 3 occurrences of this pattern in the text. Okay, so that's the basic question we want to solve in this area. Given the pattern and the text, find the occurrences of the pattern. And most of the time, we will want to find the leftmost, the first occurrence. So again, I had to break this text into lines, but it's a sequence, right? It's one sequence. Okay, makes sense? That's pattern matching. So I'm sure you have seen this before. So this is the basic question. And I will also give you some historical background for all the things I'm talking about. Okay, so that's the pattern of length m, and the text is of length n, and the result should be yes or no. Okay. So people look at it a long time ago, and they figure out some very efficient solutions. So the naive solution probably works in time n times m. You just check naively each possible position in the text, right? But then if your pattern is something like a, and your pattern is a but ends with b, then you will check many occurrences of this character a, and then you get stuck, right? So you have to do something clever. And you can do something clever. Maybe you know the Knuth-Morris-Pratt algorithm. Do you know, who knows that? Okay, not many people, but I will not talk about it. Ask me later if you are interested. So there are many linear time algorithms. Okay, so they take the pattern that they the text, and in time n plus m they output the occurrences. In fact, all occurrences. And what's maybe a little bit surprising, actually, some of the later algorithms, not the Knuth-Morris-Pratt algorithm, but the more advanced ones, actually use only constant space. So you have this pattern, you have the text, and you can read any character in the pattern in the text in constant time, right? So you have random access, and then you use like 5 variables on top of that, and that's it. But that's quite difficult. It uses some combinatorics on words, and I'm not going to talk about it. But if you're interested, ask me, and I can give you the reference. It's quite interesting that you can do that. It's not obvious, at least I think. Okay, so that's the exact. No, there is also an easy randomized one, the Karp-Rabin algorithm, but there is a deterministic one as well, which works in a different way. The Karp-Rabin is not so complicated, you just compute those rolling hashes, but there is a deterministic. I mean, there are many of them. I'm not sure who was the first. I don't want to tell you because maybe I'm wrong. Okay. So this is the exact pattern matching, and it's interesting. And when you actually look at your favorite programming language, probably you have a function which does that. In C++, you have str function. In Java, there is also something else. So it's all implemented. And actually, some of them implement this constant space algorithm. Not all of them do that correctly. But for instance, in C++, it was broken for quite a few years until they got it to work correctly. Okay, so that's the exact version, but real life is not so exact. We have some noise in the data. We have some errors. And we would like to still solve the same problem. We would like to find fragments of the text that look similar to the pattern. Okay, so it's not exact occurrences, but something which looks almost like your pattern. So now you have to define precisely what does it mean to look similar to the pattern. So you need to introduce some notion of similarity. Okay, and there are a few ways you could do that. Okay, so again, the same example. And for instance, you could ask about occurrences, so fragments of the text of length m, yeah, that match with the pattern everywhere except for one position. So you have at most one mismatch. Okay, so you look at a fragment of the text of length m, and you start comparing it with the pattern character by character, and you would like to have just at most one position where they differ, and everywhere else is the same. Okay, make sense? So again, the same example. With the new definition, we will get this additional occurrence where you have k, j, a instead of f, right? But otherwise, it's the same characters. Yeah. So we have one more occurrence with at most one mismatch. Okay. So that's the first version. Okay. This is quite natural. But again, when you think about real data, then the noise might be not only that you change a character, but maybe some character disappears for some reason, right? Because you didn't manage to capture it. So a more general version is that you want to find occurrences of your pattern with one error. And let me define what error means. So it means that either you change a character, so that's one error, or you delete a character, or you introduce a new character, you insert a character. So like in edit distance, that I'm sure you know it from your basic algorithms course, right? So that's the same definition. No, you would pay 2. But people also look at this swap distance, but I don't have it on the slides. It's a bit more annoying to work with this. Okay, and here we have, I guess, one more occurrence because what? Because this KJFTASL can be obtained from your pattern by removing k, character k. Okay, so there is one more occurrence when you allow errors. Okay, makes sense? So those are just definitions of what you could do, and there are some other versions. So you could ask for swaps. You could allow moving longer blocks of characters. So you could say that you pay 1, and you can take a substring of your pattern and move it into different places. So there are more generalizations, but they are a bit more complicated to work with, so I will stick with those 2. In fact, I will talk mostly about mismatches because they have a very nice structure. Okay, so we would like to solve pattern matching with mismatches in some good context, because the exact version is pretty much solved. So you cannot publish. Okay, so we have pattern matching with mismatches. So now the input is your pattern, your text, and this parameter k, which is how many mismatches you allow, and you would like to find the occurrences of the pattern in the text with at most k mismatches. And in the other version, this parameter k is the number of errors that you allow. So now your complexity depends on 3 numbers, k, m, en, and we try to figure out what's the best complexity in terms of those 2 parameters that you could get. Okay, again, errors is just the added distance, the usual added distance. You could also introduce some weights in your added distance and so on and so forth, but let's not do that. So what is known for those 2 versions? I will give you a brief summary of history, and I will show you one algorithm in a minute. So for mismatches, the first algorithm was by Landau and Wishkin some time ago. So it worked in n times k, and I will show you how it works in a few minutes. Okay, so if your k is small, your running time is close to linear. So and if your k is large, probably you don't really care about those occurrences because there is so much noise in your data that you just don't care. Okay, so we would like to parameterize by k, and for small k, we would like to have good running time. Okay. And there was also an algorithm by Abrahamson which does not depend on k, so it works efficiently for large values of k. So in particular, you can choose your k to be m, and it beats the naive n times m algorithm. So it runs in n times root m log m. Okay. And then there were some more complicated complexities. I'm not going to read that. So the important message is that so this Ambler-Levenstein-Porat, it's an improvement on Abrahamson. So instead of m, they put k. And the other algorithms, they run in linear time if your k is small enough. So for instance, you can say that my k is at most m to 1/3, yeah? And then this third algorithm will work in almost linear time, like n log n. Yeah? So for small values of k, they run in linear time. And then this dependency, this threshold on linear and non-linear has been improved a few times. And I will show you this last algorithm, but probably after lunch. Okay? So that's for mismatches. And for errors, there are not so many results. So there is this n times m, which is you just use dynamic programming like you do for the distance. You change it a little bit and it works. So probably you can see it if you think for 2 minutes. Then you can also do n times k. It's by the same guys that did the n times k for mismatches, but the algorithm is a little bit different, but also not very complicated. And then I'm not going to read that complexity. It's, so they use something called deterministic coin tossing, which you might know from your parallel algorithm course. And then you get this log star when you use this method, and they do many more things. So it's weird complexity. And finally, there was an algorithm by Kodan Hariharan, which again is very efficient if your k is small. So if you set your k to be m to 1/4, it will run in linear time. Okay, so for small k and for any distance, it's very efficient. So this last algorithm is, I think it's the best known. There is a conjecture that it works in n times k to the third, but no one was able to prove this conjecture. So if you want to think about something, you can read it and think. Okay. So let's try to do something for mismatches. So let's try to do something better than the naive algorithm. So the naive algorithm is n times m. Sorry, say again? Say again? Yeah, k is how many errors you allow. Errors is like insert, delete, or substitute a single character, like in any distance. So one error is that you can insert a new character, you can delete a character, or you can change a character into a different character. And you pay 1 for each of those 3 operations. And k is how many times you can repeat that. Okay? Huh? That you can get n times k to the power of 3 for the last one, by some maybe not so large modification of the algorithm, but the algorithm is very complicated, so no one was able to do that. So it uses periodicity properties very heavily, and it's very, very difficult to analyze because you need to look at combinatorics, but not of exact occurrences, but of any distance, and then the combinatorics is much more complicated. Like the periodicity and things like that are more annoying. Okay, so mismatches. So let's try to do pattern matching with mismatches. And I will show you how to do this n times root of m log m. Okay, so we'll try to beat n times m. So now the setting is that I don't care so much about k. For each position in the text, I want to compute how many mismatches I would have if I put my pattern right there. Okay, so I have all possible, I will call it alignments of the pattern in the text. So just think about starting positions. And for each of those starting positions, I want to compute how many mismatches I would get if I put my pattern there. Okay, that's the setting. So it's more general than on the previous slides. All right. So this third one, I'm not sure, honestly, because I never managed to understand it. But the others find a representation of all occurrences. I guess the third one will also do that, but I don't know. I don't know. But I will talk about finding one for most of the time. Okay? Mm-hmm. Okay, let me show you. Yeah, I think, yes. I mean that I take a substring of the text. I will talk about mismatches, only about mismatches. So the algorithm will be for mismatches. For the distance, you have to change the definition a little bit. But for mismatches, you just take a substring of length m. And there is nothing weird happening with the definition. Okay, so let me just draw it again. So this is your text. And you put your pattern. Yes, of course. So this is your text, right? This is your pattern. You put your pattern at position I in the text, and you count how many mismatches do I have, and you should output it for each I. Okay, so you need to output n minus m plus 1 numbers, and that's your output. All right, and you want to do something not too stupid. Yeah. The stupid thing would be just n times n. All right. So we will use a tool, which you probably know. We will use polynomial multiplication. So do you know FFT? Who knows FFT? Or have you heard? Okay, good. So still, I'll explain the slide, but it's good that you know it. So we will work with two polynomials. So if you have a polynomial of degree n and the other polynomial of degree m, then you define the product of two polynomials. So that's just the standard definition, right? So nothing weird is happening yet. And using FFT, you can compute all those coefficients in the product, right? That's what FFT does. It multiplies to polynomial, okay? And actually, I will think that polynomials are vectors. So I will think that one of them is a vector a0, a1 up to an, and the other is a vector b0, b1 up to bm. And I will think about convolution, where convolution is a third vector, where I put the coefficients of the product of those two polynomials. Okay, so I will think that FFT takes two vectors and outputs the third vector. Okay, and this is what you can do with FFT. Okay, makes sense that you can, and FFT works in, well, linear logarithmic times. So in n plus m times log of n plus m, you will get the convolution of those two vectors. Okay, so that's the basic tool we will use. Now the question is, how do you use polynomial? How do you use this convolution in a string problem? What's the trick? Okay, so let me show you. Make sense? This what's FFT and what? Okay, so let's make first a simplified assumption. So I would like to think that the length of my text is at most 2m. Okay, why I would like to do that? Because I want to have just one parameter in my complexity, so it's a bit easier to look at. Okay, so what I do a very simple thing. I take my text and I partition it into blocks of length m. Okay, I just cut it into blocks of length m. And now I observe that any occurrence of the pattern, any alignment, is fully contained in two consecutive blocks, right? So what I can do...
Could you now explain why you can reduce it to n plus?
Yes. Yes. And from now on, I will work with text of length at most 2m, so it will be a bit simpler to look at. Okay, so I cut my text into blocks of length m, and I just say that if you have an alignment of the pattern, it's fully contained in two consecutive blocks, right? Because, make sense? So it means that I can take the first two blocks and solve my problem on those two, on the concatenation of those two blocks, right? Then I can take the second and the third block and solve the same problem on the concatenation, and so on and so forth. So I reduce my problem for pattern of length m and text of length n to n over m problems where the pattern is still of length m and the text is of length 2m. Okay? So very simple reduction. You do it in all those problems, so you don't worry about n. Okay, maybe you have to worry a little bit not to output the same occurrence twice. So maybe you have to cut one block by one letter, right? But you don't really care that much about reporting all of them. Okay, so now we can show a very simple algorithm which works in time size of the alphabet times m log m. So I didn't put the size of the alphabet before. So in the general case, we don't want to assume anything about the size of the alphabet. Maybe it's just binary alphabet 0, 1. Maybe it's ACGT because the motivation comes from biology, right? But maybe it's large. We don't want to assume anything. Okay. So the first algorithm, we do the following. So consider a character from the alphabet. So C is a character from the alphabet. Look at your text and your pattern. Construct two vectors. In one of them, you put 1 when C occurs at the corresponding position of the text. Okay, so you look at your text. So it consists of some characters A, B, A, D, C, right? And whenever you see a C, you put 1. If you see something else, you output 0. And that's how you construct a vector for your text. And for the pattern, you do the same. Okay, so I will call that characteristic vectors for the text and for the pattern. Okay, so just from those two strings, I obtained two Boolean vectors. Okay, Okay, and now I claim that if I convolute those vectors, then I will get something meaningful, hopefully. Okay, so I take those two vectors and I convolute them. So let us think, what does it mean? This we don't need. So I claim that it will allow me to compute for each alignment how many matches I get that concern character C. So I have some alignment, and I would like to sum up for over all positions in this alignment how many pairs of characters are the same. And I claim that this convolution will tell us, well, how many pairs of characters I have there, such that both of them are C. Okay, so it's a very simple observation. Makes sense what I want to do? Now you can see that what I wrote here is, what I said, is not exactly correct. I have to reverse one of those vectors, because otherwise I will get something really weird. So let me just draw, okay, makes sense? More or less? Let me just draw it again. And I have character C here. And I also have character C here, okay? And I want to construct those two vectors so that such a pair of characters will give me +1 here in the resulting vector. Okay? So what do I need to do that? Well, so this is some position J in the pattern, right? In the vector for the pattern, I should just do what I said and reverse it. And then at position I plus m in the resulting vector, I will get the sum over all those characters C. Make sense, more or less? Or not so much? Not so much? Who could follow what I said?
Sorry, can you repeat again? So, but if we convolute these two vectors, then in position I will have...
Okay, let me do it again. So we have an occurrence of character C in the text. It's at position I. It's at position I, okay? And I have an occurrence of character C in the pattern. It's at position J. So what I would like to do is to increase by 1 the result for position I plus m minus j. Okay, so I have, let's call it C. Yeah, so I have this array, this vector C, where I put all the, maybe C is not the best name for it, yeah, but let's keep it. Okay, so I would like to increase it by 1. Why? Because if I put my pattern here, so that those two occurrences of characters seem match with each other, then this occurrence of the pattern ends at position I plus m minus j. Right? That's where it ends. Yeah, because this is j this is of length m, and at position j I have an occurrence of character C. And at position I in the text, I have also an occurrence of character C. Okay, so if I go to the right by m minus j positions, I will get where this occurrence ends. Okay, makes more sense now? Yes? Who can see what I... Okay, some people. Okay, so I would like to increase the result, the answer for position I plus m minus j. But if you look at the definition of the convolution, in the convolution I take AI and BJ, and I increase the answer for CI plus j. Right? That's how convolution works. So it means that in the second vector B, I have to just reverse it. So instead of j, I need to have m minus j. And then by convoluting those two vectors, I will get my vector C, where for each ending position of an alignment, I get how many positions in the pattern match with characters C in both places.
Sorry, why there is not CI plus j?
So this is a possible occurrence of the pattern. Okay, it starts somewhere here, and this is position j in the pattern, and this is position I in the text. So now, where does this possible occurrence end in the text? So this is position I in the text, and what's this distance from position j in the pattern to the last position in the pattern? It's m minus j. Yeah, from here to here, I have m minus j positions. And those two occurrences are aligned with each other. So I have to go to position I in the pattern, in the text, and go to the right by m minus j positions. Okay? We can talk later if it doesn't make sense. Okay, so that gives you some algorithm. And for each letter of the alphabet, you have to repeat to run FFT. Yeah? So it will be very slow if the size of the alphabet is large. Right? So for binary alphabet, you have nice complexity, but for large alphabet, you have something quite stupid. Okay, so now what you could do if your alphabet is large.
So is it true that if the alphabet is large, we can replace I mean, can we replace size of sigma by log size of sigma?
That's not, in fact, I will show you that probably not. I will show you, that's the only conditional lower bound that I will do today, and I will show you that probably not. You will get something, but it doesn't count mismatches if you want to put characters. I guess you wanted to put just the characters, the binary encoding of the characters in the, but then the result that you get doesn't count mismatches. It counts something. For exact matches, you would get the same answer, but here
you mean we cannot filter out?
You will get some noise there. It won't be the. It will only capture the exact matches, but I guess, but nothing more. Okay, so what to do if the alphabet is large? So the intuition is that if your character C occurs very few times in your pattern, maybe it doesn't occur at all in the pattern, just in the text, then it doesn't make any sense to run this convolution for that character, right? Because you don't get any information. Similarly, if your character C occurs just twice in the pattern, you have spent so much time computing its matches, but it occurs just twice in the pattern. So maybe you can do something completely different for this character that occurs just once or twice. Okay, that's the intuition. You want to do you want to play two games. One game you play for characters that occur many times, and for them you will spend lots of time. And the other game you will play for characters that occur very few times. Yeah, so that's the kind of balance that you get. So what you can do exactly? So you split the characters into two types. One is heavy and the other is light. Or you can choose some other name if you prefer. And we separately count for every alignment of the pattern in the text how many matches you get from heavy characters and from how many matches you get from light characters. Okay? So for each alignment you want to compute this one number, which is the number of matching pairs of characters. And you split this number into two numbers. One is the heavy characters contribute to one of them, and the light characters contribute to the other. Okay? And by summing up those two numbers, you will get the result. Okay. So what you can do exactly here? So if you have a heavy character C, oh, I didn't tell you. A character is heavy if it occurs many times. So there is some threshold S. And we will adjust S in the end of this algorithm. Okay? So if your character is heavy, then you just run this convolution scheme. So you pay m log m for this heavy character. Okay? That's what you do for heavy characters. Now, why it's not so stupid? Because a character is heavy when it occurs at least S times in the pattern. But the pattern is of length m. So how many heavy characters you can have? M over S, right? So if you choose your S to be large enough, you will get very few invocations of this FFT. Okay, so that's the first case. And the second case is that you want to count the light matches for each alignment. Okay, so how you do that? Well, so you look at each position in your text. Let me just remove this, maybe. So you consider the positions in your text one by one. And let's say that here you have position I, and you have character C at that position, and it's a light character. So it occurs few times in the pattern. Okay? And now you want to calculate how many matches it will generate for all possible alignments. So what do you need to do to generate a match? Well, you have to take your pattern. That's your pattern. And you have to align it in such a way that this C is above some occurrence of C in your pattern. Okay, so in your pattern you have a few occurrences of C, you don't really know how many of them. And now you have to choose one of them, let's say the middle one, and you need to align your pattern so that they both match. Okay? And then you have to increase the answer for this ending position. Okay? So we just do this. So it's a very naive approach. For each position I in the text such that Ti is light, we iterate over all occurrences of Ti in the pattern. Yeah, so we iterate over all three of them in this case. And for each of them, we increase the answer for the corresponding ending position of this alignment. Okay? And that's it. Why it's not so stupid? Well, because we do that only when Ti is a light character, and then it has only S occurrences in the pattern. So you for each position in the text, you will spend at most all of S time. Okay? Make sense? So it's a simple algorithm. And now you can probably already see that it gives you this n times root m log m. You just have to adjust S appropriately. So you write down the complexity. So the complexity is m over S times m log m. So you noticed already that you will get that from the convolution, right? That's how many times you run it. And then for the other case, you pay m times S. Because again, we assume that the length of the text is at most 2m. Right? So you have at most, you have all of m positions in the text, and for each of them you spend time S. So you optimize, you choose S, and you get this complexity. Okay? And this is what Abrahamson did quite long time ago. Okay? Make sense? So this is a simple algorithm. But this trick, this idea of splitting into two cases, sometimes three cases, it appears over and over in those problems. So sometimes you have to introduce more classes of matches, and for each of them you need to come up with some clever trick, but a different trick for each of them, and then you optimize over all possible thresholds. Yeah? So that's why I wanted to show it to you. Okay? So now the question is, can you do better than that? So Abrahamson did that in '87, so it has been quite some time. So by now someone should have, figured it out. So can you beat this complexity? So now I will try to convince you. So no one could. So it's the best known complexity for this case. The situation is different when you introduce this parameter k. For small k, you can get better complexity. But if what you want to do is to count for each possible alignment the number of mismatches exactly, that's the best you can do. So let me show you some excuse for why this is the best we can do. Okay, make sense so far? Yes? Okay, so let me show you a reduction. So reduction will be from matrix multiplication. Okay, so we have this problem of Boolean matrix multiplication, where you get two matrices, n times n, so this square matrices, and you want to just multiply them, the usual definition of multiplication. And there are Booleans. Okay, so now the question is, why would you use such a problem? Why would you want to reduce from such a problem? So that's the question to you, maybe. How fast you can multiply to such matrices? What do you know? Well, the naive algorithm works in n to the power of 3 complexity, right?
Boolean means that 1 plus 1 is 1.
Yes. No, sorry. It's not that 2. It means 1 plus 1 is 2. It's actually OR. It's the same ring, not the. We can think that we multiply them over reals or integers, or what we want in the end is that to have an OR of end. So it's the Boolean sum ring, but we can lift to integers. Okay, so this is what this is the problem that we have. We know how to solve it n cubes time. It's a naive algorithm, but probably you also know Chassens or maybe one of the more clever ones. So they can do it much faster. So the best known, I don't know what's the best known, n to 2 point something. It changes every month. Yeah. Maybe not every month, but last month there was something like third digit after the. Okay, so there are some clever algorithms for that. Now now there is this notion of combinatorial algorithms. So what is a combinatorial algorithm? Essentially, it's a bit funny definition. It's an algorithm that doesn't use any of those fancy Strassen and better algorithms, right? So the precise definition is not so clear what's a combinatorial, but there is there are some people who try to design non-combinatorial algorithms, and for again, the definition is not clear. I will discuss it in more detail in a few minutes. And for this combinatorial algorithm, the best they can do is, I think, n to the power of 3 over log to the 4, so they can shave some log factors if they don't use this Strassen or better algorithm. Okay. So, and this is the reason why sometimes people try to use this as a conjecture. So they try to say that, okay, let's assume that you cannot solve this, you cannot multiply two Boolean matrices with a combinatorial algorithm, and let's try to see what you can infer from that. Now the question is, what's the message that you will get from such a reasoning? Essentially, you will get a message that in your algorithm you should use Strassen or one of those algorithms, because otherwise you cannot really improve. So if you can improve the algorithm for your problem, you will improve the algorithm for matrix multiplication. Okay, I will discuss it a bit more, but now let's look at the reduction. Okay, so in the reduction, you give me two matrices, right? And I want to construct my pattern and my text in such a way so that when you compute the number of mismatches or the number of matches, it's the same thing here, for each possible alignment, then from those results, I'll be able to reconstruct the product of A and B. Okay, so I want to design my text and the pattern so that given all the scores for all alignments, I will know what's the product of those two matrices. Okay, so now how you can try to do that? So you have to come up with some clever gadgets, as you seen yesterday, right? So here it's I guess a bit simpler. All right, so I claim that the following will work. So first I take A, and I spell out its elements row by row. So I go row by row. So R1 is the first row, then R2 is the second row, and so on and so forth. So I write them down, and I separate them with some special character. So I have this sharp or whatever it is the right pronunciation for that. Okay. And additionally, I put a bunch of special characters in the beginning and in the end, just to separate things. Yeah? So it's not really important what happens in the beginning and in the end. But now here is a small trick. So when I write down the elements in in the ith row, I do the following. When the corresponding entry of A is 0, I write 0. But when the corresponding entry is 1 of A, I put the column number. Okay, so again, I should draw something. So I have my row, it's the ith row in A. I look at its elements. If it's 0, I output 0. If it's 1, I output the column number. Okay? And for each row, I do the same. For each row of A. And that's how I construct my text T. Now for the pattern, you can guess that I should do the other way around. Yeah? So I should look at each possible column and write the elements column by column. So again, C1 is the first column, and so on and so forth. And I do a similar trick, which is that if I look at a column here, if I have a 0,
could you please clarify? So I just lost somewhere in there. So R1 is one row or one
yes.
symbol?
Ri is one row. So I think about a row as a vector of length n, Ri, and I look at its elements one by one. I should do a small example. I'm not sure if it's a good example, but so if my A is something like that, then for the first row, I will output 0, 0, 3. For the second, then I put the separator. Then I have the second row, so I output 1, 0, 3 again, and separator. And then I output 1, 0, 0, and a bunch of separators in the beginning and in the end. Okay, that's what I do for A. And for B, I play a symmetric game, but I look at columns. So for each entry, I output, so here it's 0 prime. I output 0 prime, which means some special character. So the zeros in row zeros and column zeros are different zeros. So special characters. Maybe 0 is not the best choice for it. Okay? So, and for each a 0 here and a 0 here, they don't really create a 1 in the product. So I don't want them to contribute anything. So that's why I used two special characters. Okay? Now let us check that this reduction does something. On the previous slide. And now I claim that I can reconstruct each entry of the product by looking at some particular alignment and by looking at whether I have a match or not there. So you can see that I will have lots of mismatches because I put those zeros and zeros prime. Yeah, so probably in most of the positions I will get lots of mismatches, but sometimes I will get a match. And I claim that whenever I have a match, it tells us something about some entry in the product of those two matrices. Okay? So now let us think, when do I get a match? When I can generate a match? So those special sharp characters, they cannot create a match because they occur only in the text, right? So they don't create anything. Those zeros and zero prime characters, they don't create a match because they are different characters. So the only possibility for a match is that I have 1 in some row of A and 1 in some column of B. And then they are aligned with each other. And moreover, it should be the same character. So I should have, okay, so it means that I have, let me draw it. And some column here. And I try to figure out when do I have a match. So to have a match, I should have some character K here, and the same character here in the column, right? Otherwise, I cannot get a match. But then, because here I put K in column K, and here I put K in row K, it means that the only way I can get a match is that if it's the same K, right? The same column and the same row here. Otherwise, I cannot get a match. Okay? Make sense? Because again, character K here occurs only in column K, and character K here occurs only in row K, nowhere else. Okay? So now I claim that so okay, it's clear that it's the only way I can get a match. And now you can also see that because I put those, oh, actually, I think I made a mistake. Those special sharp characters in the pattern, they shouldn't be there. So in the pattern, I just concatenate. I don't put any special characters. That's P should be just C1, C2 up to Cn without any separators. Yeah, just the text. Okay, so now I claim that because I put the separators in the text, then the matches correspond to the entries of the product of those two matrices. And now, why is it so? You have to just, so when you have row I here, and column J here, then you have exactly one alignment when one is above the other. Okay? And all other CJs in the pattern, they cannot be matched with some RI. Because because you have those special characters, those special sharp characters. So what I mean, let me just draw it. So here you have Ri, some row of the matrix A, and here you have Cj, some column of the matrix B, right? So and one is above the other. And then because you have those special characters here in the text, but you don't put them in the pattern, then for every other column encoding and row encoding in the text and the pattern for this alignment, they cannot match. They cannot generate even a single match. Okay, because they are.
So there is not only one sharp, but also square of n sharps.
No, just one. Just one is enough because here you are out of sync by one. Look here. The previous block here and the previous block here. They're out of sync by one, and this is already enough for them. Because what character you put depends on the position modulo n, here and there, and they cannot match. Okay? Make some sense?
Yes. But
I and j, then I can look. I can look up the score for some particular alignment, and I look whether it's 0 or something larger than 0. If it's and it's larger than 0, if and only if, for at least one value of k, I have one here and one here, which means that I can recover the entry of the product by looking at a particular alignment. Okay?
Right. So at this point, I don't understand why we need these caches that in the text, actually.
Because otherwise, for different values of I and j, I would increase the answer for the same alignment.
So what do you mean by saying by?
I'm saying that if you give me I and j, row and column,
Just compute the corresponding alignment.
yeah, and it's different for each I and j.
Right.
And otherwise, it wouldn't be different. Because, yeah, without this here, so the starting position of the alignment where I want to extract my answer from is here. But the starting position of the alignment for I minus 1 and j minus 1 would be the same alignment. So they would both contribute to the same alignment. So I would only know whether at least one of them is 1. But for each of them, I need to know separately. Otherwise, I could still do something from triangle detection, maybe, so for some more specific problem. But here, I just want matrix multiplication. Okay, makes sense why I need those special characters and why I made a mistake on the slide. Okay? Mm-hmm.
Is it true that
Yes, I will need a different reduction. I will show you that after lunch. So this works only for square matrices because I have adjusted the parameters. And we will want rectangular matrices to get a more general statement. But after lunch it's easier to convince you, to get you to agree. Okay, makes sense? Okay, so that's what we have shown. So we have, what exactly we have shown? We have shown that there is no combinatorial algorithm that can beat m to 1.5 by something significant, yeah? Because there is this conjecture that there is no combinatorial algorithm for multiplying two matrices in better complexity, right? But now it gets a little bit, okay, makes sense that we have reduced matrix multiplication to our problem. But now, of course, we do know some better algorithms for matrix multiplication, right? So we need to restrict ourselves to this notion of combinatorial, which is not set in stone exactly. So it's possible that there's an algorithm that is non-combinatorial. And now the question is, what does it mean to be non-combinatorial? So the usual definition is to use matrix multiplication. And if you recall this algorithm, this n times root m log m, it uses FFT. And now it's the question to you whether you think it's combinatorial or not, because FFT is also, you know, I don't know. So the question is, can you do something better using maybe matrix multiplication or some similar methods here? So it's not no, okay? So I just want to mention that. And let me show you one very simple trick in the last 5 minutes, and I guess we can. Do you have 5 minutes?
we reduce the problem to matrix multiplication?
The other way around. We reduce matrix multiplication to our problem. So if you can beat the complexity for our problem, you have something for multiplying matrices. So in particular, you can plug in the best known exponent for matrix multiplication, and you will get something that it's not known how to beat m to 1.12 something for our problem, because otherwise you could beat the complexity for matrix multiplication, which people work a lot, and it gets more. No, I mean that. This reduction didn't use the algorithm is combinatorial. So what you can say that if you can come up with something better for our problem, then you have something better for matrix multiplication. But the best known bounds for matrix multiplication, there are this n to 2.3 something. So you would get so if you can get m to 1.001 for our problem, you would get something very, very good for matrix multiplication, which people don't know how to do. Okay. But they don't know, which doesn't mean that it doesn't exist, right? So it's okay. So let me show you one simple thing. So we will use suffix tree. Do you know what suffix tree is? Who knows what suffix tree is? Oh, good, very good. I don't have to I'll just show you a picture. Made a figure with banana. So banana. And it's known how to construct it in linear time. Maybe you know it, how to construct it in linear time. And then usually you put some additional information on it. And one of the usual tools is lowest common ancestors for trees. Who knows lowest common ancestors for trees? Okay, many people. Good. So given two nodes in a tree, they tell you what's the nearest node that is ancestor of both of them. And when you do that on the suffix tree, you get this very nice primitive which allows you to take any two. The primitive that we are going to use. So probably we have seen it a few times, right? We have implemented that. I don't know. With those LCA queries. So you iterate over all possible starting positions in your text. So I is a starting position. And you start to compare one by one. Yeah? So you just start comparing characters. Okay. But that's quite slow because the pattern is of length m. So what you can do is that you start at position I in the text and at position 1 in the pattern. And you compute the longest common prefix of those two words. So this green region is supposed to be equal. And using suffix tree built for the text and the pattern, you can get in constant time how many characters match. So you get the first mismatch, this red character A and B. And then you just continue after A and B. So you use longest common prefix query, and in constant time you jump to the next mismatch. Okay, and you repeat. How many times do you repeat? Well, k times, k plus 1. Because after each iteration, finds you one mismatch. So after you have found more than k mismatches, you don't care. There are so many of them that you don't care. Okay, so for each position in the text, you need to ask k plus 1 longest common prefix queries, and each of them you can answer in constant time using this LCA machinery. So that gives you n times k algorithm. Okay, so it's very simple. Make sense what we're doing? And for some reason, it's called Kangaroo Jumping. I have no idea what's the story behind it, but I didn't put the picture of kangaroo. Okay, so after lunch, we will see. We'll try to figure out whether that's the best you can do. Yeah. So we will try to look at the dependency between n and k and m. And yeah, we see that if your k is up to m, then probably you cannot beat n times root m log m, under those assumptions about combinatorial algorithms. But now we don't know whether n times k is the best you can do. Maybe you can do something better, right? So we will see that later. And I will show you just one thing so that you can think about something during your lunch. We will need this one tool. There are two notions of approximate pattern matching in general. I mean, one of them was that you allow k mismatches or k errors, so that's why I'm discussing. But there is also another notion, which is maybe more natural when you are coming from approximation algorithm perspective, is that you want to approximate this number. Yeah? So for each alignment, you have this one number, the number of mismatches or the number of errors. So now you don't want to compute exactly, you want to approximate within a factor of 2 or within a factor of 1.001. So there is some epsilon, right? And for each alignment, you want to output number, di, which approximates the number of mismatches. So it's between 1 minus epsilon times the real answer, and it's no larger than 1 plus epsilon times the real answer. And you would like to compute that for each position I. So try to think a little bit how you could do that, and we will use that later as a building block. Okay, and I guess that's for the time being it's so. Unless you have questions.
Can you why we can't call the Strassel algorithm combinatorial?
We don't call it combinatorial.
Yes.
That's a good question, and no one really. I don't know. I'm not an expert on that, but it seems that this notion is not so precise. So I mean, one thing that you do in Strassen, you start with Boolean sum ring, but then you move it to integers. And maybe that's, I don't really know. I mean, I don't really know. It's, I wasn't able to find like very precise.
So it's just like a common argument and you won't go deeply.
Yeah, yeah. I mean, those reductions are being used. They're not so usual as the orthogonal vectors, but just something people. So for me, it's an indication. You should look at the other direction. You should think that maybe now this is an argument for why you should try to use matrix multiplication for your problem. Such a reduction, right? Because now you went into one direction, so now maybe it's an indication. In fact, there are some examples where people first did such reductions, so they show that their problem is at least as difficult as matrix multiplication, and then they said, oh, so now no combinatorial algorithm can beat what we have, and later they thought, oh, but actually we can do something non-combinatorial, but they wouldn't start doing that problem if they hadn't found this reduction earlier, because it gives you some intuition where to look for algorithm. What type of methods yeah, but it's not so precise. I mean, yeah. So at least I think it's not so precise. Maybe, yeah.
Yes, there is this open problem of solving triangle detection like without multiplying matrices. And then this means, I mean, the challenge is to find a combinatorial algorithm for triangle detection. And by saying combinatorial, they usually mean that you do not multiply matrices.
Yeah, it's a bit of maybe I don't know. But so they do some very interesting things to design those combinatorial algorithms. So they can shape logs, and they use some very nice machinery to do that. Yeah, I can send you some references later. So the notion is not so. Yeah, I think it's not.
So what is the current running time for combinatorial matrix multiplication?
I think the best known is n cubed divided by log to the fourth. It's from 2 or 3 years ago. Maybe it was improved, but n to the power of 3 divided by the fourth power of log. So divided by one log, it's very simple. You just use the 4 rations technique, divide it into blocks. And then I think 2 logs is also not so, I don't remember. And then there was paperwork by Williams and someone else, and they used some very heavy machinery to shape a little bit more, like really heavy machinery. Like this Semeredi regulatory lemma, like some. Sorry? For rectangular. Oh, you mean it uses rectangular? Just n times n to 0.2 that you can multiply. But also some Semeredi type argument, no? Maybe it's a. So this is something that I think people like. I mean, because there has been a series of paper inventions. Yeah. So but they don't define so precisely. I think, at least maybe I didn't understand them.
Thank you.